Now that we've learned about parallel loops and the for all construct, let's see how we can apply it to a very common linear algebra algorithm, and that's called matrix multiplication. So, the idea behind multiplication of two dense matrices is that let's say you have two matrices A and B that you want to multiply into a result C. An element Cij of the result matrix is the inner product of row I and column j, row I of array matrix A and column j of matrix B. And that can be expressed mathematically as a summation k going from 0 to n minus 1 of aik times bkj. Now, our interest is in running this computation in parallel. It's very important to support linear algebra packages that solve a number of important problems in practice. And in fact, this is the kind of computation that's even used to measure the speed of the fastest computers in the world. If you look for a popular website called Top 500, you'll see that the underlying benchmark is really a variation of matrix multiply. So, how will we convert this first to sequential code? And we'll go for a simple algorithm here, not a complicated one like Strasson's. So, what we could do is say we can iterate through I and j, and we'll write these more high level for loops. So, we've got a two-dimensional space for I and j, and what we want to do is we want to compute for a given I and j the element Cij. So, what we could do is we could assign Cij to 0 and then add a new loop k that iterates to 0 to n minus 1 as well, and accumulates the inner product by doing aik times bkj. So, this is pretty much a direct translation of the math formula into sequential code. Now, from the viewpoint of parallelism, let's think about which loops can run in parallel. For the I and j loops, we see that each element of a matrix C can be computed independently. So, we can very conveniently actually say instead of a sequential for, we can have a for all. And this works in general across multiple dimensions. It's saying that all n squared iterations for I and j can all be run independently. So, what about the k loop? Can we run it in parallel? Well, there's an issue over there, because if you imagine all these k iterations running in parallel for the same Cij, each k iteration can read and write the same Cij, and that would lead to a data race, as we've discussed earlier. So, we have to keep this k loop as sequential. So, what we've seen is that very commonly used and important dense matrix computation like matrix multiply can be expressed in sequential loops directly from the math formula. And once you have the sequential loops, you can identify which loops could be converted to parallel loops in the form of for all. And here there is abundant parallelism with order of n square parallelism for an n cubed computation. So, this gives you a very simple example to work with, and we look at more examples in the exercises that accompany this module.